Today we're going to look at a limiting reagent theoretical yield problem using two different approaches. The first approach is going to be my way, and then subsequently we're going to look at the ALEKS approach. In my approach to solving this problem, which isn't just my approach, incidentally, it's a very common way of explaining it and the way you'll see in the textbook. The first thing you do is you write a balanced equation. ALEKS is fond of giving you combustion type reactions to write a balanced equation. There are also some problems that are acid-base neutralization. There may be others, but these are the two main ones. So the first thing you have to do is write a balanced equation. The next thing you have to do is to convert each reactant to moles of reactant and then use the mole to mole ratio to get moles of product. The third step is to decide whichever produces less product is limiting, meaning whichever reactant produces the lesser amount of product, we can identify that as our limiting reagent. Then once we know the maximum amount of product that we can possibly have, we take that mole amount and we convert it to grams. So let's go through this step by step. First, take a close look at the problem. Ethane reacts with oxygen gas to produce carbon dioxide and water. Classic combustion problem. We react 12.9 grams of ethane with 66.9 grams of oxygen gas. So our first job is to write the balanced equation, and here it is. It ends up being 2 moles of ethane react with 7 moles of oxygen to produce 4 moles of carbon dioxide and 6 moles of water. In step 2, we take each gram amount of reactant. Grams of ethane divided by its molar mass gives moles of ethane. Then we use the mole to mole ratio between carbon dioxide, our product, and ethane, our reactant, to find out that the most product this could possibly produce is 0.858 mole of CO2. We repeat this exercise, importantly, with oxygen. We take our 66.9 grams of oxygen, we divide by the molar mass, this gives us moles of oxygen. Then we use the mole to mole ratio for CO2 to oxygen, which is 4 to 7, and we find out in this case we could potentially produce 1.19 moles of CO2. Thing is after we have produced 0.858 moles of CO2, C2H6 will have run out, so we can't make any more. This means that this is the maximum amount of product we can have, and ethane must be limiting. Since ethane is our limiting reagent, we say, okay, 0.858 moles of CO2 times its molar mass gives us 37.8 grams of CO2, and that, ladies and gentlemen, is our theoretical yield. Take 2 is to look at this the ALEKS way. It's somewhat similar, but also substantially different. We do start, as always, writing a balanced equation. Another similarity is we take each gram amount of reactant and convert that to moles of reactant. Now there is a departure. In the ALEKS way, you actually compare reactants using the mole to mole ratio between reactants. In my way, you used the mole to mole ratio between product and reactant. Here you're using mole to mole ratio between reactants. In this case, you have to evaluate which reactant will run out first by comparing moles of reactant to one another. Then you use the moles of reactant that are limiting to get moles of product and convert that to grams. Once again, we have our balanced equation. We take grams of C2H6 ethane and convert to moles of ethane. From there, the strategy is that we take 7 moles of O2, compared to 2 moles of ethane, that's our mole-to-mole ratio between reactants, to find out that we need approximately 1.5 moles of oxygen to react with 0.429 moles of ethane. We do that again for oxygen. We get moles of oxygen and say, okay, we need 2 moles of ethane to react with 7 moles of oxygen. That means we need 0.597 moles of ethane to react with this much oxygen. Now comes the tricky part. Which one of these reactants is going to run out first? ALEKS uses subtraction tables. This is both a lot of work and maybe not completely necessary if you recognize what the gist is here. We can say, looking at these two calculations, that we need 0.597 moles of ethane to react with the available amount of oxygen, which is 2.091 mole. We don't actually have 0.597 moles of ethane because in our first calculation, we realized that we only have 0.429 moles of ethane based on the gram amount of ethane available. So clearly, this is going to be limiting. Let me just show you this thought process another way. We need 1.501 moles of oxygen to react with 0.429 moles of ethane. Do we have it? Yes, we have more than enough oxygen to provide the 1.501 mole. So oxygen must be in excess. From there, we can proceed to step 5 and say, okay, 0.429 moles of ethane will produce a certain amount of carbon dioxide based on the mole-to-mole ratio. 4 moles of CO2 will be generated for every 2 moles of ethane used. And then once we have that, we simply multiply by the molar mass of carbon dioxide, and we get the same answer we did the last time. There are more calculations, I have no doubt, in this instance than what I showed you using my approach. However, if you like the ALEKS way, you can certainly use it. Which way? My way? The ALEKS way? The highway? Whatever you do, pick a lane. Do not confuse the approach demonstrated in lecture and in the textbook with the ALEKS explanation. Either one, if deployed correctly, will give you the right answer. You just have to decide which one makes sense to you and practice it. That will provide you with the correct answer.